this video, we're going to talk about X-rays. We're going to talk about how X-rays are produced, how they're used, and how they actually can create an image. So first of all, in order to produce X-rays, we need to have a cathode. So a cathode, as you may have seen in like an electron tube or something like that, works as like a heated filament, which we then accelerate electrons from across a gap. And in the case of a production of X-rays, is that the electrons are accelerated and caused to strike a anode over here. They strike an anode. Now, the action of striking that anode causes them to slow down. So the electrons slow. Now, there's a specific property of what happens when electrons slow down, or when any particle slows down, really. But in this case, when this one slows down, it releases its energy, and the energy released is in the form of photons. So photons get released, and in the case here, the energy that these electrons have releases photons of a range of wavelengths. But with the energies, we're expecting lots of X-rays. Now, naturally, you would expect there to be other wavelengths or frequencies based on the energy that the electron had. But if we have X-rays that are not strong enough, then obviously they wouldn't be able to penetrate the body and so create the images that you're probably all aware of. So what ends up happening is we look to actually filter those out through a screen or some aluminium. So filters out unneeded photons. So it's the X-rays that have a high enough energy are the ones that we want to hit the person or the patient to be able to create images of bones and say other objects as well in the body, and so we can see if they have any problems. So the next stage is to take those X-rays. So here's our X-rays here. Coming in, and here's the person or patient that needs to be imaged, or the part of the body that needs to be imaged. And so what happens next is these X-rays will effectively be absorbed by the material that is in their way, but they won't be absorbed by other bits of material, say flesh and organs, and so they will not get absorbed, and the screen behind them shows and absorbs the unabsorbed X-rays, the bits that have gone through the flesh, but it will not pick up the ones that did not, because they did not go through the bone. So as a result of this, we see an outline or an image of the bone that does not allow the X-rays to travel through. So there are two words you need to be aware of that go with X-ray images, and one is contrast. So contrast is the word we use to describe the wide variety of shades of black, which allows us to see the different materials. So if you see lots of different shades of black, and you'll see this in lesson, then that's telling you that all those different materials have different thicknesses or are of a different material that absorbs X-rays differently. Okay, so that's what contrast allows. It allows you to contrast all of the different materials that you might be shining these X-rays through. The other side of it is sharpness. Sharpness allows for edges to be seen really clearly. So say, for example, the edges of bones are really well defined. That would mean it was a sharp image, as opposed to, say, for example, a blurry image. A blurry image is one where you wouldn't be able to see the edges of the bone very well and you wouldn't be able to tell where they were. So contrast allows you to see the different types of material through different shades of the black, whereas sharpness allows you to see the edges of the object in question really clearly. Now, in order to do this, there is an equation, one that you will probably be familiar with in structure, but not necessarily in terms of the values that's used, looking at attenuation. So the intensity that we get out when we pass through a material is equal to the initial intensity, e to the power of negative mu x. Apologies, I've not drawn that great. Okay, so that's a mu. And again, you'll have seen this kind of form of equation in radioactivity, because in radioactivity, we use this style of equation for half-life. Very similar here. We actually use this value x is the thickness of the material. When we talked about radioactive decay, this was time, and there was such a thing called half-life, and that was the time taken for the number, the activity to drop by a half. Well, believe it or not, there is such a thing as a half thickness, which is x half. So we call that the half thickness. And that is the thickness required of a certain material to drop the intensity to 50% of its original value. So the half thickness allows for a 50% drop of intensity. And so as a result of that, we can actually use very similar equations in the kind of use of this, for example, the same as we did in radioactivity. We'll come to that in a second. So the half thickness is a value that sometimes can be measured for a specific material, but the specific material is defined really by this value of mu right here. So mu is the linear attenuation coefficient, which basically tells you, because remember attenuation is kind of like how much the intensity drops. So this is a factor that allows you to work out by how much the intensity is going to drop. So for the purposes of seeing this graphically, you will see here that you have a thickness, the intensity and your thickness on this side. And if you were to measure over an amount of thickness of a specific material, you get a graph like that. And again, we've seen graphs like this nice negative exponential decay function graph here that we've got, which allows us to effectively show the half thickness. So the thickness required to drop the intensity by half is the half thickness, which is where that comes from. And you'll see that thought process very similar in radioactivity and nuclear decay as well. So it happens exactly the same physics concept, but not in terms of the root of the physics here. So where we go from here is the things that you might be aware of is the relationship between these two values that you can get, that ln2 will be equal to mu x half, okay, which allows you to work out if given one of these values, you could work out the other. So knowing the linear attenuation coefficient, you can work out using this equation what the half thickness of this material is, the thickness required to reduce the intensity of the X-rays to half. So very, very standard kind of format here, ln2 equals mu x half. So very similar to, like I said, radioactivity. And you'll be able to put some of these equations and concepts into use, thinking about contrast, thinking about sharpness, and going forward from there. Okay, so we'll have a look at these in lesson, and we'll have a look at some of the kinds of questions you might get asked about X-rays then.